Good morning. This will cover our presentation on a lake water condensing unit. My name is Ernesto Batista.
My name is Dominguez.
And I'm Hilario Hernandez. For our problem statement, we want to replace a residential air conditioning condenser with a lake water cooled condensing unit. Our goal is to design and manufacture a full-scale 4-ton lake water cooled condensing unit and water pumping system. We will use lake water instead of air to cool the refrigerant gas exiting the compressor. For our motivation, we want to use the advantages that water cooling has over air cooling, which include water's higher specific heat capacity, density, and thermal conductivity. We want to reduce energy consumption and use a renewable energy source for power. Here you have the components of an air-cooled condensing unit, which includes a fan, an air-cooled coil, and a compressor. We're going to replace the fan with a water pump, the air-cooled coil with a coaxial heat exchanger, and the compressors will stay the same. This schematic shows the vapor compression cycle and a water-cooled condenser. The refrigerant gas leaves the compressor as a high-temperature, high-pressure gas. It flows through the condenser where it is cooled from the lake water, with the lake water, and exits with a phase change as a high-temperature, high-pressure liquid. It then flows through an expansion valve where it rapidly cools and flows through an evaporator. In the evaporator, your warm air from your home gets cooled. Also, there's another phase change, and the refrigerant is now leaving the evaporator as a low-temperature, low-pressure gas. At that point, it returns to the compressor where the cycle starts again. This is our proposed design flow diagram. Energy from the sun is converted to electricity, which charges a battery. The battery powers a pump. The pump draws water from the lake and flows through the outer coil of the condenser. Hot refrigerant gas leaves the compressor and flows through the inner coil of the condenser. Heat exchange takes place, it condenses, and you have your high temperature, high pressure liquid exiting the coil.
The idea of air conditioning was first introduced in the 1840s by Dr. John Gary. He believed that cooling the temperature from a hospital room will help to avoid diseases such as malaria, although it wasn't until 1902 that the engineer Willis Carrier invented the first modern air conditioning by creating an apparatus that was able to control the humidity in the air. These systems were too big to be incorporated in a house. Therefore, while working for General Electric, Frank Faust invented the first self-contained residential room cooler in 1929. During the evolution of air conditioning, there was an energy crisis in the 1970s. For that reason, laws and standards have been created in order to regulate the production of these systems and to protect the environment. In order for the design of our coil, we're complying with the standards from the Heating, Air Conditioning, and Refrigeration Institute. We also consider the standards from the American Society of Mechanical Engineers. To be more specific, we're going to use the standard 1983 from ASHRAE, which basically established how to run our methods of testing and what equipment should be used in order to collect our data. We'll also look into the standards NFPA 90A and NFPA 90B, which basically covers installation, maintenance, and operation of these systems in order to avoid life or property from any damage from fire, smoke, or gases produced from fire. For our analysis, we're going to use the following heat rate equation in order to determine the heat rate for the coaxial heat exchanger that we're going to use, where S here is our shape factor, given the fact that the geometry of our coil is going to be an eccentric circular cylinder. In order to determine which pump we're going to use for our system, we're going to use Bernoulli's principle, and we're going to apply to the following equation, where it's going to be established at 2 points of the pump. In this case, in this picture, you can see the inlet and outlet ports of the pump. We're going to calculate the losses of our system using the loss head equation, where our friction factor can be determined based on the fluid flow, if it's either turbulent or laminar, and we also, it's going to be based on the roughness of the material selected for the piping. We're also going to account for any losses to the fittings of our system Once we get the final value for our total hydraulic head, we're gonna plug that value into a graph versus flow rate, and we're gonna estimate our best efficiency point, and from there we're gonna select a pump.
As part of the alternative designs, we are including a different source of coolant, which can be well water instead of lake water. Another alternative would be placing the coil that carries the refrigerant inside the lake. This would avoid the need for a pump or an outer coil. There's also a possibility of using a different material for the outer coil of the heat exchanger. We have chosen PVC because of its low cost. For the simulations that need to be performed on our CAD design, we have included the heat transfer simulation, which would predict the efficiency of our entire system, and the water flow simulation, which would help us validate our pump selection and give us a clear idea of the effect of this flow inside our pipes. As far as the global issues that apply to our design, we're making sure no chemicals get in contact with the water by using a coaxial heat exchanger similar to the one in the picture that would run the water and the refrigerant through 2 individual pipes. Because we're using copper as our main material, and as I mentioned before, PVC as an alternative material, none of this would introduce any contaminants to the water. Another environmental concern was the high temperatures of the water back in the lake, but we have done some testing on the existing air cool condensing unit to check the temperatures at which the refrigerant goes in and out of the system, and based on the data obtained, we can say that it shouldn't be a hazard to the environment. Our manual would be written in English, Spanish, and French to address the largest market possible, and we will be using the US customary units and international system of units. As far as safety, we're planning on placing labels everywhere they're needed to easy assembling of our unit and scheduling testing and inspection of our unit before it is in use. Because we're using the thermal capabilities of water over air, our unit will be a lot more efficient than the existing air-cooled condenser. We have designed a smaller unit, so we will need less material for manufacturing, and our coil will be a lot shorter, so the refrigerant required for the system will be less. Here is a rough breakdown of the main components that we will need for our prototype. I have included the pump, the coaxial heat exchanger, compressor, solar panel, and battery bank. And compared to the typical residential condensing unit, we are cutting costs by about $250 just in manufacturing.
Up to this point, this is an illustration of our project timeline. We have come up with a concept design. We have collected some data, such as the temperature from the water lake, and also the inlet and outlet temperature from the existing coil, the 4-ton condenser unit. We have more work to do over the fall and the summer of fall. During this project, we have been able to engage in some learning experiences. We have expanded our knowledge in HVAC systems, which can be used in future projects. We are also raising awareness of current world issues such as global warming, as well as we are implementing our time management and communication skills.
So up to this point, we have come up with the main concept design and 3 alternative designs for our project. Some of the data we obtained from testing the temperature in the lake and the temperature of the refrigerant on the air-cooled condenser has helped us confirm our initial assumptions and theories. And we still need to run all of the simulations on our CAD design and do some more analysis before we go into manufacturing. With this, we conclude our presentation. We hope you enjoy it, and we open the floor for questions.
One question I have is, why aren't you looking at salt water too? I mean, we are coastal, and it's almost salt.
We thought about it, but we were talking about how much more maintenance that would bring to the whole system compared to the well water or the lake water.
But there's a lot more people that live along the coast, at least in Florida,
Yes,
that live in Okeechobee.
That would be also
That's an alternative that we actually thought about, but since the residence that we have access to is on a lake, we're mainly designing for that. knowing that it expands. You look at well water, you look at salt water, you look at brackish water. Any water that's available should be a viable source as far as.
Well, you can come to, I live on a canal and you can come to my
That
house.
would,
and
that
test
would
it.
be.
Canal as well, yeah. But knowing that the salt water is a totally different composition of water, the materials involved would also have to be different. We did some initial searching and it'd be a lot more expensive because they usually use titanium-based or titanium-covered metals for a condenser of that. For that.
Yeah, because salt water is very
Very
close.
close.
You know, you can't even keep a boat from rusting.
Yeah, yeah. The boats actually use some stainless steel. They used to use a lot of stainless steel, now they're titanium coated, and even that doesn't last forever.
316 stainless is the
Yeah.
most, but even that'll rust.
Yeah.
So. Just a market expander though.
Exactly. Yeah.
What type of solar cells are you guys thinking of using?
For now,
Solar.
photovoltaic, and it's least expensive that we can get that'll do the job pretty much. The main factor as far as the power is going to be after we determine the size of the pump. That's the main thing. Once we have the size of the pump, the requirements that it needs, we will size the electrical power source.
I would say for your final report, it would be interesting. Maybe you want to make your model for the freshwater, but also do some research on what you would have to change your model to take it to saltwater. Because, you know, from Key West to
A
Jacksonville,
lot of houses on the coast.
we have a lot of coastal areas here.
For sure, for sure. Yes.
My question is tied to what is the total delta temperature that you're expecting the coil to be able to support?
The existing coil right now, we're looking at delta T of about 50 degrees Fahrenheit.
50 degrees, and that's assuming 100% efficiency of the secondary coil to the primary coil,
Right.
which you won't have. So obviously you'll need more than that. What type of, have you looked at the fluctuation in temperature in lakes, and will you be able to pull that much heat out of the system?
Yes, we have ran, actually right now I have a temperature probe in the lake, and we built data loggers for the specific purpose, and they're still kind of rough, so I'm still playing around with them, but I've been able to gather roughly about 18 hours worth of data, you know, from 9 o'clock in the morning till whenever the battery turned off at night, and we're able to get ambient temperature versus the lake water temperature, and we've seen that the lake water temperature during the day is significantly cooler than ambient temperature, which is what your air cooled
How significant?
in order of
15
about
degrees?
15, 20 degrees sometimes.
15,
yes.
20.
Depending, it all depends on from what I've seen, the temperature at night and how cool it is at that night. It'll stay a lot more stable as far as the temperature is concerned. You know, your graph for your day temperature goes up and basically comes down. The graph for the lake water temperature is almost straight, even it goes up after afternoon at night. That's when the temperature starts actually rising. But it's a lot more efficient.
And then again in August or September, where are you going to be at?
I'll be there testing that
You'll
out.
be there testing?
It's my
Okay.
house, so it better work, right?
Okay. I noticed on your org chart, your testing finishes up in December. Again, as I gave somebody else the advice, I suggest you bring it in, figure out how to pull your testing back a little bit, give yourselves the ability to look at your data, analyze it, and tell us why it is perfectly an analog to what you expected, or what your expectations of why it deviates.
Yeah.
And I strongly suggest that all be done before November's over,
Yeah.
because December just will fly by. So that's just too late. And then the last thing is bifouling. What are you going to do to make sure that the system is assurances that you don't get this thing all clogged up?
All clogged up. That's a very interesting point. We're in the process of trying to figure out how we'll possibly incorporate a flushing system, just using house water to flush it either manually or automatically, just on a regular basis to make sure that we don't have that. That is something that I thought about, because during the winter we don't use the air conditioning as much, so the water in the pipes is going to be stale, or it could stale up quite a bit.
We grow a lot of stuff in
Yeah.
pipes here.
Exactly. So we were thinking about running some kind of automated system where it would just flush the system, or run the system without having a need to, without the air conditioning actually be on, just run the pump to remove the system, the stuff going in the system, to flush itself out.
Okay, thank you.
Thank you.